Hi, everyone. Welcome to Team 21's interim presentation. Our team members are Connor McNabney, Emerson Kekua, Nick Corper, Ben Maskell, Jim Woodford, and Zach Jarsky. For our project, we chose to analyze and redesign a toaster oven. As a background on our product, we're analyzing a Mainstays 4-slice toaster oven used for toasting, baking, and reheating food. It has about an 8 by 10 inch capacity that's heated by 2 quartz rods as heating elements. For temperature and time control, there are 2 knobs on the control panel for adjustable settings. We estimate that the production volume is approximately 100,000 toasters per year, assuming a 1% market share of 9.6 million toasters total. The primary customer group is personal and household use by families in their kitchens at home, and the secondary customer group is commercial use by employers such as restaurants.
Here's an exploded view of our product with all non-fastener components shown and numbered. And also note that we did not include any electrical components like circuit boards or wires. Our fast diagram shown in this slide shows the functions that the toaster oven must perform in order to heat food, which is the main function. And we have 2 main functive branches that relate to heating food, one being containing the food and then heating the interior.
So assembly sequence 1 starts with the inner case. The heating elements and the heating element guards are attached to the inner case spanning its length. The bottom plate and its associated components are inserted next. Then the control panel with its knobs and LED light are attached to the front of the inner case. Then the back plate and its stabilizer braces are attached. Then the door assembly is added next, and the assembly is rounded off by the heat sink plate attached to the top, then the outer case. Moving on to assembly 2, this is different slightly in that after the bottom plate comes the door, then the control panel, then the back plate. In assembly 1, it is the control plate, then the back plate, then the door. So that's how the sequence differs.
After comparing the 2 sequences, our team found sequence 2 to be more advantageous due to the ease of fastening joints and testing subassemblies. Therefore, we will proceed with sequence 2.
Function component mapping matrix shows the different components of the product and their respective function from the fast chart. As can be seen, some items have more than one function, which is inefficient and can be a reason for a possible redesign.
For the bill of materials, the CAD model showed 30 distinct components, mostly unique geometry sheet metal parts. We decided to consider purchasing sub-assemblies for the heating elements and also chose to purchase the LED lights, screws, springs, and rivets from McMaster. Beyond sheet metal working, we chose injection molding for the plastic components. All of the assembly processes made sense to perform manually due to some of the intricate features involved. Material costs were the highest for the large stainless steel cases, $55 to $60 each, due to the material cost for the 18 gauge 304 stainless steel that we chose as it appeared to be industry standard for commercial appliances. We assumed a 25% scrap rate for sheet metal and 10% for injection molding. We also assumed $120,000 for stamping die, forming dies, $250,000 for injection molding dies, and $55,000 for lathes. With the die life of 500,000 parts, we needed 96 sets of tooling. For an annual volume of 100,000 units, which is 1% of the market and a 5-year payback, we calculated the tooling costs for sheet metal working, turning, and injection molding. This totaled to $416.18 for the estimated manufacturing costs compared to the retail values of $679 to $750 for the commercial grade version of this unit. For the quad chart, we classified the components as shown. The lower cost but higher functional importance items included many of the components related to the structure and inner workings of the oven. The low functional importance but high cost items included the control knob and LED light.
The differentiating table shows the different functions that would be available for the 2 models, specifically controlling the temperature and time. And the module that would change for these items would be replacing the knobs to a touchscreen control plate, which can be shown on the next slide, where you can see on the right the new plate would, or touchscreen would replace the knobs on the left.
Here's a common interface table that shows the various components that can be modified without affecting the design of other components, as long as they still use the standard interface shown in the right-hand column.
In the original assembly sequence, the control plate is assembled earlier than necessary. As the control plate contains the modification between our two products, it is beneficial to extend this assembly stage to a later point in the product family design sequence. This can be seen in the modified assembly sequence below.